Okay, thanks, Loic. So I'm going to be talking today about multi-object spectroscopy with JWST. And in particular, this is really key because this is the first time that we've ever had a multi-object spectrograph in space. And so it's going to be able to do some quite amazing stuff. So I'm going to start off talking a little bit about what the multi-object spectroscopy mode is with the NIRSpec instrument on JWST. And then we'll move on to the APT and do a demo of how you might actually use the APT, the astronomer's proposal tool, to set up a MOS observation. Okay, so let's start with the MSA and some of the characteristics of it. So what we have here is you have a fixed grid of micro shutters. So these are tiny little shutters. There's 250,000 of them, and each one is addressable to be individually opened or closed. So by doing that, you can basically open just those you want to, and that lets light fall through the instrument to be dispersed onto the detector only in certain small regions of the sky. So that avoids you getting the whole sky background that you might get in a slitless spectroscopy mode, which leads to higher sensitivity. So each of these little micro shutters, if you project it onto the sky, the shutter is about 0.2 arc seconds wide by 0.45 arc seconds high. So given the PSF of JWST, it's very good for fitting in a single star or a single compact galaxy. There are 4 quadrants of micro shutter arrays. I'll show you the layout a little bit later. But in total, the total field of view covered from end to end is 3.6 by 3.4 arc minutes. So it's quite a substantial field of view. So those of you used to working with Hubble, it's about the same as the ACS imaging field of view. There are 2 detectors, almost identical detectors. They're the same 1 to 5 micron detectors that are used in NIRISS and in the long wavelength arms of NIRCam. So the same style of detectors, and that gives you a full spectral range from about 0.6 to 5.3 microns. There are 2 different dispersing elements or types of dispersing elements. There's a prism, and that gives you the full wavelength coverage over this whole range at which the detector is sensitive, but at a low resolution. So the resolution there is approximately 100, but it actually varies quite a lot across the wavelength range. So if you look at the chart on the right there, you can see the prism is the green curve at the bottom, and in the 1 to 2 micron range, the resolution is well below 100. But then when you get out to the 4 to 5 micron range, it's actually more like 2 to 300. So it does change quite a bit over the wavelength range. But then you get the whole spectrum in one go. If you want higher resolution, then there are order blocking filters and gratings in 3 different bands and at 2 different resolutions. So there's an R of 1000. These are the M gratings on the figure on the right-hand side. And there's R of 2700 in the high resolution gratings. So each of those resolution settings, if you want to get the full spectrum from 1 to 5 microns, will need to make 3 observations, 1 with each of the gratings. If you're going to use the MSA, because there is this fixed grid of very small shutters, you really have to have very good astrometry to be able to position your targets exactly in the shutters as expected. So if you use typical ground-based data, you're not going to be able to register the positions of all the different objects on the field well enough to be able to make sure that you're getting a significant fraction of the light coming into the shutters. So in general, the astrometry should be better than about 15 milliarc seconds. And in general, you get this only from space-based Hubble type imaging and not from data from the ground. So I'll talk a bit more about those requirements later. If there are any questions on the way through, please feel free to interrupt and ask a question. Okay, so showing you a bit about what the NIRSpec focal plane looks like. In the back, in the light green, are the 2 detectors, which are labeled here as 491 and SCA 491 and SCA 492. And then the darker green in the middle shows you the 4 micro shutter quadrants that basically cover a smaller region because obviously the spectra will then disperse out from either side of the micro shutters, the dispersion direction being horizontal in this plane and the spatial direction being vertical. So you can see that in between the 4 micro shutters, there are a couple of gaps to think about. In the vertical direction, there is a gap where there are fixed slits and the IFU aperture. So the IFU is covered in a previous webinar. There's also fixed slits, and those basically are all drilled out of a plate that lies in between the micro shutters. So there is a fairly large gap in that region. That means that if you're observing a field, there will be a large gap in the middle where you can't place any targets. And then looking in the other direction, there is a gap between the micro shutters and also between the detectors, just because you can't butt the detectors right up against each other. So there is a gap of 18 arc seconds there, and that will have consequences because if you place your targets in one of the micro shutter quadrants, then in many cases, some of the spectrum will actually lie within that gap where the detectors are. So it's important to consider that if you're planning an observation, that there may be some regions of the wavelength range you don't get because of the detector gap. Okay, and if you were to place some high-resolution spectra on the field here, this is how they would look. So this is the R2700, where we've opened some shutters in the micro shutters, and these are where the spectra lie. And then the little red dots over on the left-hand side, these are 0th order, which you get with the gratings. And so right now, the way things are set up, all the 0th order fall on the detector, but they fall off the interesting parts of the detector where the spectra are lying. So you won't get any contamination there. And now if we move on to look at some real data, this is test data at the R1000 mode in the band 1, or the shortest wavelength, 1 to 7 micron grating. And what we see here is, as you can see from the previous plot, there's the 4 MSA quadrants which have spectra in them. There's the fixed slit region in the center, where you can see spectra from all of the fixed slits. And if you look at in the MSA quadrants, you can see that each spectrum is made up of several components vertically. This is by opening neighboring shutters to form what's called a slitlet. So you have multiple shutters that you open next to each other, and that basically gives you a larger region. And that is one of the main ways in which background subtraction is done and I'll talk a bit more about how you use that later. A couple of other features to note here. On the right-hand side, there is some arrows pointing to fail to open single shutters. So as I'll come on to in a minute, unfortunately, the technical details of how you construct this tiny little micro shutter array proved to be quite challenging, and it isn't 100% perfect. And there are some shutters that have failed both in the closed and in the open sense. And those are important to take account of when you're planning an observation. So this is called the MSA operability map. So this is basically showing you which parts of the MSA are not functioning correctly for you to be able to use to place targets. So all the black lines here are basically things that are essentially failed closed in one way or another, which means that you can't use those shutters to open up. They're always going to be closed for all observations. So they take the form of individual shutters, little groupings of multiple shutters, like the kind of little squares you can see, or little rectangles, and also rows and columns. So the rows and columns are due to electrical shorts, where basically the entire row or the entire column is now put out of use and is not able to be used. So in total, the operability map shows us that about 13% of the shutters cannot be opened. So this is a significant amount. It's a very large number of shutters, but it still leaves enough shutters that can be opened that you can get a very large number of spectra onto the field of view. The other thing to note in the operability map, you don't actually see them in the operability map, but they're shown here by red circles where they are located, are the failed open shutters. So these ones are much more dangerous than the failed closed, because the problem with the failed open is they're always going to be open whether you want to open them or not. And that means that the background from the zodiacal light from the sky is always going to come through, and it's going to contaminate the spectrum of any other object you try to put along that same row. So we have to know where the failed opens are, and we then have to make sure that we don't plan to observe things that overlap with those regions of high background. The failed open, because it's only 20, it still covers a very small fraction of the total field and doesn't limit things too much. Okay, so how do we use the microshutter array to actually make an observation? Here you see the default observing strategy, which is where we open several shutters next to each other, making what is termed a slitlet. So the things on the left-hand side here, where you have a red shutter and then green either side, these are slitlets that are formed by opening 3 shutters at the same time. And the way that this diagram's laid out, you basically, if you work from the top down, you have a slitlet of 3, then you have another slitlet of 3, then you have a gap because there's a failed open shutter, and you don't want any light from that failed open falling onto the same row as where your shutters are. And then there's another slitlet of 3, then another one, which is the one that's kind of zoomed into on the right side, and then another one. And so in these cases, the failed closed shutters aren't impacting us because we don't want to open any of those shutters anyway. If you have a target that's where it would lie right next to a failed closed, then you may not be able to open a full slitlet of 3 shutters. The thing about the diagram on the left here is that it is idealized in that because of distortion across the full size of each quadrant, you don't actually get things lining up in this neat way where the 3 shutters lie neatly butt up one against the other, and you can end up getting overlapping spectra if you don't leave a somewhat larger space between the slitlets in some cases. So certainly distortion needs to be taken account of, and that's why there's a complete tool to plan the observations like this, instead of you just having to open up whichever shutters you feel like opening to make your own slitlets. So if we look at what's going on the right-hand side now, and this is how we do the default background subtraction. So the default is that you would open 3 shutters to make a slitlet for each small source target that you have that really just fits in 1 shutter. And then what you do is you nod the telescope up and down so that the target moves from 1 shutter to the neighboring shutter during the course of the observation. So in this example, we have the target in A is in the top shutter, in B is in the middle, and then in C is in the lower shutter. And then to do the background, you can do the background subtraction either in space or in time, depending on how constant the background is over time. So you would basically be just subtracting the pixels from 1 shutter from its neighbor, probably in time will be the best way of doing it. And this allows you to get very accurate background subtraction because, and also dealing with the detector noise, because you're subtracting from exactly the same pixels the background noise level from where your target was in the preceding observation. Okay, so because of this, even though if your targets are small, you're probably going to want to allocate 3 slitlets or about that to each target so that you can get very good background subtraction. If you try to pack too many targets on without leaving enough space for background, then you will get spectra of many objects, but you may not be able to calibrate those properly and subtract off the background. Okay, so this is basically nodding. What's termed nodding is this making slitlets and moving the telescope up and down to move the target from 1 shutter to the next. As well as nodding, we have dithering. So dithering is basically a larger scale move, and it's designed for to improve the sampling or increase cosmetics, basically by putting the spectrum into a totally different part of the detector. It could also be very useful for other things through background subtraction and flux accuracy, depending upon the size of the dithers. So there are 2 ways in which we use the MPT, the MSA planning tool, to do dithers. There are fixed dithering patterns, or there are flexible dithering patterns. The fixed dithering patterns, they're recommended when you have fairly small dithers. So we're looking at things around about an arc-second here. And then you set up one MSA configuration of deciding which shutters to open onto your targets. And then you make a small offset and change the MSA configuration to open basically the neighboring slitlets in each case. So you'll basically take the whole pattern that you've already designed on the MSA, and then you translate that to a the very same pattern, but moved slightly, and then move the telescope accordingly. In this mode, the attempt is to get all sources observed at each point. And the only times that fails is when you hit shutters that are fail closed, for example. Then you may not be able to open all the shutters again. And an illustration of the fixed dithering patterns is shown on the right. So when you're using fixed dithering patterns, you're basically defining the offset in terms of the number of shutters in both the spatial and the dispersion direction. On the other hand, flexible dithering patterns are used if you want to get a larger offset. Because as soon as you move beyond a fairly small offset, there's going to be distortion. That means that sources that were centered in one of your shutters in the original configuration aren't centered anymore in the later configuration. So because of that, as soon as you go to any larger dithers, you really have to go to flexible dithering patterns. And what you do with a flexible dithering pattern is specify basically a range over which you want to search for the offsets, both in the spatial and in the dispersion direction. And then the MSA planning tool will basically go and find all the configurations that can be used that observe your sources as often as possible. So it doesn't come up with exactly the same configuration, just translated to a different position, the same way that the fixed dithering patterns does. It's basically much more free to have totally different MSA configurations in each of the different dithers. But as I say, it's absolutely essential for large dithers. Yes?
Sorry to interrupt. Is there a science case that, in which science case would you prefer fixed or flexible dithering?
Well, I mean, it really depends upon how much you want to move over the field. So one of the reasons you might want to move over the field is if you require continuous wavelength coverage. As I mentioned before, that there are these gaps between the detectors. So if you only do a fixed dithering pattern with a small size, you're not covering that 18 arcsecond gap between the detectors. So if you want to actually cover that gap so that you get the full wavelength coverage, then you'd be better off doing the flexible dithering pattern. The downside, though, is that you're not going to get the same galaxies the whole time, or stars in the MSA configuration once you do the flexible dithering patterns. Because of distortion, some sources that were well centered in shutters will then be moved off to the edges of the shutters.
Okay, thanks.
Okay, any other questions? No. Okay. So this is a slide that you'll have seen if you've been following the other webinars already. And this is talking about how to make an exposure with these near-infrared detectors with JWST. So basically you make an integration where you're sampling groups as you go up the ramp. And NIRSpec works in this same mode as well. So in this case, we have NG is kind of the main parameter you're going to be looking at, which is the number of groups in the integration, and then NF is whether we're actually averaging frames during this group. NIRCam has a lot of these, a lot of different patterns used to read out. With NIRSpec, it's quite a bit simpler, and there's just 4. So the thing about NIRSpec is that because we have a low background, particularly when at the higher spectral, the medium and high spectral resolution with the gratings, NIRSpec's always detector noise limited. So that means it's very important to understand that the effects of the detector noise, and even with the prism, some wavelengths with some exposure times, you're still detector noise limited. So in general, what that means is you want to go for the longest exposure times you can. And you can use the exposure time calculator to play around and see what the effect is of whether you do lots of short exposures or a few long exposures. But you'll find that you'll want to do long exposures of order 1,000 seconds if you can. And the recommendation is that you do somewhere between 1,000 and 1,500 seconds per exposure, as long as that gives you enough nods and dither positions to be able to do the science for the total time required. You don't really want to be doing very short exposures here, unless you're dealing with bright objects where you're not detector noise limited because there's enough signal from the source itself. So the two basic readout patterns are very similar to the ones you may have seen already in the webinar. So that's the rapid mode, where it reads out with no group averaging every 10.7 seconds. And then the NRS mode is where we average over 4 frames in each group. And then the frame time is 42.8 seconds. In addition to that, NIRSpec is the only instrument that has a special readout mode called IRS². And this stands for Improved Reference Pixel Sampling. And so what's done here is that while the detector is being read out, there's extra samples of the reference pixels. And those are used basically to do a quicker reference pixel correction than is done standardly with the near-infrared detectors. And what that means is because you're sampling the reference pixels more often, you can reduce the 1/f stripe noise. And because NIRSpec is background limited and so often in these cases, it's very important to be able to reduce that noise. And particularly, it's a stripe noise that's correlated, and that can be particularly bad when you're trying to do spectroscopy. So in general, it's recommended that if you have reasonably long integrations and you're background limited, you're best off using the IRS² mode. But you can only use IRS² if you're in full frame readout using the whole array, which is always the case if you're doing the multi-object spectroscopy. Okay, so target acquisition. I mentioned before that you need to have good astrometry if you're going to be able to use the MSA to its fullest potential, because you have to put the sources that you're targeting exactly into these shutters. So there are a few different target acquisition types called here optimal, relaxed, and verify only. You generally want to be doing the optimal for most science. This gives you the best possible photometric accuracy. And for that, you need to have a catalog with very good relative astrometry. It says 5 milliarcseconds here. You can get away with a little bit worse than that. And the idea is that that will give you target acquisition accuracy less than 0.1 shutter width, which essentially means that you pretty much know exactly where you're putting each target into each shutter. So you do require for this reference stars, which are measured on the same astrometry system as the targets. So ideally, you want an image from something like HST or from one of the JWST instruments where you're measuring the stars and your science targets exactly on the same image. So you're able to get the astrometry of the reference stars compared to the science targets as accurately as possible. The relaxed mode is basically if you have slightly worse astrometry at 40 milliarcsecond level. So this may be something kind of astrometry you can get to from good ground-based data. But in this case, you can't position things accurately to within the same fraction of a shutter. So if you have extended sources, it may not be such an issue, because with extended sources, you're still going to hit a significant part of the source, even if you have this astrometric inaccuracy. It also, for example, would give, if they're less well centered, you don't really know so well where each target is. So it makes it difficult for you to do the slit loss correction with the MSA if you don't know exactly where in the MSA the target was placed. So there are some issues if you don't have the good enough astrometry. And then the verify only, is not using any reference stars. It's just going to that position using guide star acquisition. And there we think the accuracy is approximately 100 milliarcsecond, but also there is no roll correction there. So you may not be at the same orientation quite as you think you are. And so there's really limited science you can do with that unless you have, a field where you don't really need to know exactly where it is you're pointing. One key difference here with the MSA compared to using slit masks that you might drill for ground-based telescopes is that the MSA gets reconfigured after you've done the target acquisition. So the reference stars are not taking up space on the mask. You define your reference stars, but then you can have, when you configure the MSA, you basically close the shutters where those reference stars are, so they're not going to be impacting the number of science targets you can get onto the mask. So you can really have as many as you want, and it's recommended to have up to 20. And obviously spread across the field is important as well. If all the reference stars are in one quadrant, it's going to reduce your accuracy. So observing planning using the MPT, I'll run through a complete demo of that shortly. But basically, as I mentioned, you need to have good accuracy for the input catalog, preferably from HST or from NIRCam pre-imaging. It is allowed in cycle 1 for people to apply for NIRCam imaging and then also apply for NIRSpec follow-up spectroscopy, where you use the NIRCam imaging to do the astrometry and also do target selection. So that is a mode that's been allowed, and I think it'll be very powerful to be able to follow up things that have been discovered with JWST with NIRSpec spectroscopy within cycle 1. You have to be a bit careful when you make your NIRCam observations because the geometries of the two instruments are very different. So if you want to be able to cover a significant field of view for the NIRSpec spectroscopy, you have to be careful how you define your NIRCam dithers to be able to give you the kind of image that will cover the same area. So you start with an input catalog, and then you can designate primary filler targets and also reference stars. And you can also include in there weighting so that you give higher weight to higher priority sources. You have to choose the slit-lit pattern, then choose which dispersers you're going to use, gratings or prism. Choose the pointing constraint, so how much you want to search around to find the optimal location. Then choose the dithering pattern you want, and then using the MSA planning tool, you point and place there basically is a calculation that's run that optimizes the maximum number of sources or the maximum weight if you've weighted your sources. So I'll run through all these things in the demo shortly. So one of the key things is that, as I mentioned, these shutters are very small, and so exactly how well the sources are shuttered, the sources are centered in the shutters is very important. And the difference here between the ground-based, where you drill holes at exactly the positions of your targets, and this fixed grid, is that you don't get to place all your targets in the center of each shutter. They're going to have to be spread around throughout the shutters because of just the fact that it's a fixed grid. So in the MPT, there are 5 different sizes you can set up to show how tightly you want to constrain how well centered your targets are in the shutters. So they range from unconstrained, where basically any position, even if the target is centered outside of the actual open shutter, but some of the light from the edges of the object will fall into the shutter, then that's allowed if it's unconstrained. Then they range in size as you go through open shutter area, midpoint constrained, and tightly constrained. And obviously, the more tightly you constrain the acceptance zone for where you're allowing targets to be placed, the fewer targets you'll get placed onto the micro shadow array. So it does affect your multiplexing. And then on the right-hand side, this is showing you how much light you're losing due to slit losses in a single micro shutter, depending upon how well your source is constrained. So you're looking at, if you have a very well-centered point source, when the PSF is the smallest at 1.5 microns, you are losing about 20% of the light outside the shutter. But if you go to longer wavelengths, because the PSF is larger, you're going to lose more, and so you'll be up to losing 40% of the light for a perfectly centered source at point source at 5 microns. But then if you go for objects which aren't centered, you can see how the amount of light you lose increases. And so you can see that if you go for entire open shutter area, basically the source could be located right on the edge. So its centroid could be right at the edge of a shutter. Then you're losing more than half of the light in that case. So this is something to be aware of, especially when you do your exposure time calculations, that you're not going to be getting all the light that you might expect for your point source coming through the shutters. And if you have extended sources, then things are different in that the constraints are a bit more relaxed because it's extended, so you're more likely to get some light coming through. But even if you well center it, you're going to be losing a larger fraction of the light than you would for a point source. Okay, any questions so far? Okay, well, in that case, I'll move on in a moment to the demo. So writing a JWST proposal. Proposal deadline is April the 6th, 2018. And this is the flow chart for how to write the proposal. So today, for the multi-object spectroscopy, I'm only going to be talking now about the astronomer's proposal tool. The exposure time calculator has been covered in some of these other webinars, and it's a very similar method of using the exposure time calculator that's already been discussed in previous webinars. So I'm not going to go through that today because of the amount of time that explaining the MOS mode takes. So the demo today is going to be a science case of using multi-object spectroscopy of distant galaxies. The goal is to study the evolution of galaxies at high redshift, understanding early galaxy formation, which galaxies produce the reionizing photons in the universe, and also the role of AGN. So to do that, we basically want to get NIRSpec spectroscopy of a well-selected sample of galaxies. So the Hubble Ultra Deep Field is used, which is the best small area region of the sky that's been observed. And we're going to observe at two different resolutions, at the low resolution with the prism, and also at medium resolution at R of 1,000 from 1 to 5 microns. And we're going to be nodding using a 3-shutter slitlet, and also dithering as well with a longer total integration time. The source for this is a PhotoZ catalog of the Hubble Ultra Deep Field sources from this paper by Rafalski, 2015. And this catalog is available on the webinar site. So if you want to load that catalog as an example catalog into the MPT yourself and play around, you can do that. Okay, so I'm going to get out of this now and start up the APT. So here's a blank APT. So we're going to start a new JWST proposal. I'm not going to fill in any of the stuff on the first page because that's all very generic. Similarly, the PI and COI and stuff. Targets, we don't need to identify any targets at this stage because the targets are actually going to come from the positions in the catalog. So we can skip that stage and move straight on to the observations. So we have to create a new observation folder. So we do that. And then the first thing we do is that when you create a new observation folder, you get an observation created. We don't actually want this observation because you can't plan a MOS observation by, at least not a scientific MOS observation, using this template that's been created here. So we're going to just delete that. We don't need that. What we do instead is, if you look over here, we have the observation summary tab and the MSA planning tool tab. So we're going to go to the MSA planning tool tab. Now this has 3 parts. There's catalog, planner, and plans. So you basically work from left to right, from catalogs to planner and then to plans. And then in plans, you create observations that you then see with the observation summary again. So the way to start off in the catalogs view here is to import our catalog. So we're going to import the catalog, which I know already is a white space separated catalog. And then we have to import it. And the catalog is called this, the Webinar 6 Science Case Catalog. So if we click open on that and then wait a little bit, we find that this is the catalog. So it has all these fields already here. So we have the RA, the deck. We have here a magnitude column in the F160W filter from HST. That hasn't been picked up automatically as a magnitude, but we're going to tell it now that that is one of our magnitudes. The stellarity field from S-Extractor has been picked up automatically and identified. This here is BPZ, is the Bayesian photometric redshift. This is where we have our photometric redshift estimates from the photometry. So this is our best guess of what the redshifts are for these galaxies. So we're going to call that the redshift field. And the reason why you can label some of these fields, as you'll see in a minute, is you can then use them for filtering and selecting some subsets of the sample for observation. Okay, and then additionally in this catalog, because this catalog's been set up specifically for looking at the MPT, an MPT demo, so we have this weight here, the weight field, and this basically is used for prioritization. So sources with higher weight are more likely to get allocated positions on the MSA than those without. And then we have these 3 other magnitudes here, and these are in the 3 filters, or 2 filters and a clear position for the target acquisition filters for the multi-object spectroscopy mode. So this is basically, these are pre-computed magnitudes in those filters if you want to know if your reference stars are actually going to be bright enough to observe in those filters. And then finally here, we also have reference stars labeled, whether these targets are basically stars or not.
Hey, Chris, I have a question for you.
Yep.
So can you let us know which columns are mandatory in the catalog? There are many information in this catalog, but I guess not all of them are mandatory.
Yeah, the only mandatory information is basically OA and DEC. So that's the only thing that's absolutely needed.
Okay.
If you don't have a numeric, so ID has to be numerical ID. If you have source names instead, then that won't get that can't be allocated to ID, and there'll be a new column created that is an ID number applied to each target. But basically, all you need is an RA and DEC to be able to generate a
So if we don't provide any white columns, it means that the MBT will assume the weight is uniform across the catalog?
Yes, that's right. If you don't provide weight, then everything has the same weight.
Okay, thank you.
Okay, so this is the Rafalski catalog. I'm going to call it that there. I'm going to say that when flux is used, we want to use the F160W. And so now I'm going to import the catalog. So now it's reading all the rows, and you can see there's almost 10,000 sources there. If we click on it, there's an error warning. So just because it wants some extra information, so I'm going to tell it the astrometric accuracy is 10 milliarc seconds. And this field here is for pre-image availability, basically saying, do you already have imaging of the field, or do you require more imaging in the future? So in this case, the imaging is already obtained because it's come from HST. So now what we're going to do is, so you could basically use this full list of 10,000 sources to run your catalog as your catalog. And you can see now that we have weights of 300 for the highest priority sources, but then as you go down, those quickly drop to other numbers. So we could just use this whole catalog, but the MP2 will run quicker if you have a smaller catalog, and then use the full list as fillers. So we're going to create a candidate set here with a smaller amount. So we're going to call this the Z greater than 1 set. So we're only going to choose galaxies with redshift greater than 1. So we're going to put in a minimum redshift of 1, maximum redshift of 20. Okay, and then also we're going to put in a magnitude limit using F160W. We don't want to just use really faint galaxies, or also we don't want really bright sources. So let's say we'll limit between 20 and 28 for the magnitude range. And we can then make candidate set, and you can see now we've got 3,476 sources that satisfy these constraints. Okay, so one of the things you can do is if you click on these, you can send to Aladdin. So we can use the Aladdin visualizer, and now you can see all the targets in the catalog. So this is the full Rafalski 10,000 sources, and the shape of this is just the orientation at which ACS was put for these observations, which is why it's a rotated square. And then if we go back to the redshift greater than 1 set and send that to Aladdin as well, you'll see where the higher redshift sources are located in the field, and you can see they're also spread quite uniformly across the field with a little bit of galaxy clustering thrown in. Okay, so we'll go back to here and look at the planner next. We go to the planner. First thing we need to do on the planner field is put in the position angle at which we're making this plan. So we don't know at which position angle we're actually going to make the observation. That depends on the scheduling. But in order to make a plan, we have to basically choose a position angle that works, that is observable by the observatory at some point. So it's important to note that's not necessarily the position angle at which you're going to make the final observation. But when you're submitting in phase 1, you're not defining the actual MSA configurations you're going to use, but you're simply showing an example of, the number of sources you could get, the sources you could get onto the MSA if you're, for a typical observation. But until you get the orient assigned as part of the long-range plan, closer to the time of the observations, you actually don't know exactly which orient you're going to use. And this is just an example plan. So the MPT does not optimize the position angle for you. It takes a fixed orientation you give it and has to work with that. So you have to wait a little bit now while it thinks, and it fills in this true angle to target field here. So I've chosen 45 degrees because I know from previous experience that when the instrument position angle is 45 degrees, the NIRSpec instrument field of view will line up well with this rotated square.
I have a naive question. So if we don't know the exact orient of James Webb before the observation, do we really have to bother with the MSA before actually?
Yes, yeah, you do, because you have to have an example for how many sources you can get selected. So you need to run through this whole process as if it's the real thing. And then you can say that in this example, you managed to get so many of your highest priority targets assigned shutters. If you don't run through this, then when the TAC's looking at your proposal, they will say, well, how do I know if you're actually going to be able to do what you say you want to do? Because of the particular limitations of the MSA and where you can actually get shutters opened.
I see.
Okay, so we'll set our primary candidate list as the redshift greater than 1 sources, and we'll use the full catalog as a filler list. Then if we move on to the slit setup, we're going to use, this is the default, this is using the 3-shutter slitlet. You could go to a 5-shutter slitlet if you have large objects like lower redshift galaxies that may occupy 3 of these shutters. Then you may want to move them up and down through this 5-shutter slitlet, but obviously then you'll get less targets on the MSA because each one takes up more space. You can go right down to 1 if you're feeling brave and you think you can do background subtraction in some other way. There's also an option for 2 or 3. We'll stick with 3. Then here we have this source centering constraint that I already mentioned, where there are 5 different possibilities between being completely unconstrained, you don't care where the target falls, having the target centroid fall into the entire open shutter area. We'll go with this one today. Okay, and then we have the dither setup. So we have this 3-shutter slitlet. We want to be nodding up and down in here so that we can do the background subtraction. So we'll click yes for nod in slitlet. And you can see that's telling us that we get 3 exposures per configuration. So 1 where the source is centered here, 1 here, and 1 here. And then as well as that, because we're going to be observing for longer to get enough signal to noise, we're going to do some fixed dithers. So here's where you have the choice between the fixed or flexible dithers. Today I'm just going to talk about the fixed dither option. And if you do that, then this thing pops up where you have to add a pattern. So this is basically the number of shutters. So not the number of pixels on the detector, but the number of shutters in the MSA by which you're translating your whole MSA pattern. So we'll go with 5 in the dispersion direction and 2 in the cross dispersion direction. That's approximately 1 arcsecond in each direction. And then we'll add another one, which basically follows the same pattern but goes a bit further. Another arcsecond in each direction the other way. I mean, in the same way but further. Okay, and that basically, so then we have this thing that's come here that tells us we'll have 3 configurations. So a configuration is whenever you basically configure the micro shutter array to open different shutters. So we get 3 configurations per target set, and we get 3 exposures per configuration. So this means we'll have a total of 9 exposures per grating setting. So here's where we set the grating settings. We'll start off, we will select the medium resolution, the R1000 gratings, and this is the G140M that's paired with the F100 LP blocking filter. There is also an F70 LP blocking filter for this grating, depending on whether you want to start the spectrum at 0.7 microns or 1 micron. If you've got to be aware that if you choose this one, the O70 LP, then there'll be second order overlap in your spectrum, so you've got to be able to deal with that. If you just choose the F100 LP, there's no second order overlap. And for the other filters at the longer wavelengths, there is no second order overlap. It's only this one where there's the option of, particularly because Lyman alpha in galaxies at redshifts 6 is important bit of the science of JWST, and if you choose the 100 LP, you don't get that because it's at 0.9 microns. So in those cases, you'd want the 0.7 microns. Okay, and then we select the readout pattern. As I mentioned before, we want to go for IRS squared because that gives us a better removal of the 1/f detector noise stripes. And we'll go with the rapid mode to read out as often as possible because that may well help us in mitigating the effects of cosmic rays. And the number of groups, you'll get this from running the ETC to see how long each exposure is. But basically, 65 groups in IRS squared rapid is almost 1,000 seconds of exposure time for each exposure. And we're just going to do one integration for each exposure. And now the total exposure time here is the nine integrations times 950 seconds each. Okay, but now we want to actually observe not just in this G140M, the band 1 grating, but we want to observe in bands 2 and 3 as well, so we get everything up to 5 microns. So we can duplicate this a couple of times, and then the only thing that we need to change is the grating. So we'll use the G235M and the G395M to cover the other wavelength regions. And so you can see now we've got 9 integrations in each of these 3 grating settings. Okay, moving on, the multiple sources per row. If you click this, it will open up extra shutters so that there are overlapping sources of spectra on the detector. That's dangerous to do unless you know what you're doing. So you really want to be careful, although in some science cases you may well want to do that, particularly if the continuum in these sources is faint and you think you can disentangle emission lines that come in different places, then you may want to try and get multiple sources per row with overlapping spectra. But for this example, we'll just stick with the single source per row, so there's no overlap of different spectra on the detector. Then we basically now down here, we're defining the search grid. So this shows us the area that we are planning to cover. So there's a center, and this just comes from the center of the catalog. I know from this already that the center of the catalog is going to be pretty much the center of the field if I get the 4 MSA quadrants on here, so I'll leave that as the center of my search area. And I'm not going to search over the full catalog for the center because that would really be a waste of time, because when you get right to the edge of the field, you won't get much overlap between the catalog and the source. So I'm just going to do a little search grid around the center with about 15 arc seconds. So we're going to test different pointings moving around here by up to 15 arc seconds within, so we basically change the centroid within about this region. And the step size, so this is as we step around this region, to make this go quickly, we'll set this to a fairly small number. We'll set this to 0.9. And then, so it's just going to test 324 pointings. Okay, so use weights. So this comes back to the question that was asked earlier about whether you have weights or not in your catalog. If you don't want to use weights and you want every target to be weighted equally, then you don't click there. But if you have weights like we do, where you've got some very high priority targets, for example, in this case, it's the highest redshift sources are the highest priority. So we click use weights, and then it'll basically sum the target weights, and it'll select the configuration that has the highest sum of weights. And then enable Monte Carlo. What this does, this shuffles the order of the input catalog, because the way the MPT works is it allocates shutters on a first come first served basis. So if you shuffle your catalog, you may end up getting a better solution than if you don't do any shuffling, but that takes extra time, so I'm not going to click that yet. Then we have the number of configurations, and so this is enter n times 3 for n target sets. We basically want 3 target sets, that is 3 different configurations, so we'll enter 3. If you don't enter any number there, then watch out, because if you have a very large catalog, basically the MPT will keep running until it's observed every object in your catalog, which for a catalog of thousands could take a very long time and would be very expensive in telescope time. So usually you want to constrain that to just make a certain number of configurations. Now at this point, before you can give your plan a name, so I'll call it gratings, because we're observing with gratings here, not with the prism. And then you click generate plan. But before you do that, you definitely want to save the APT file. And the reason for that is because it has been known for the MPT to crash once you invoke this plan generating component. So I've saved it now, so I'm going to generate the plan. And so now it's going to look through the primary target list of 3,400 sources, and it's going to run through these 324 different possible pointing positions, and at each one work out what the sum of the weights is to see how which is the optimum pointing position for us to place the MSA within this kind of XY grid. And for these, so this does take some time, especially if you have very large catalog size or you have a very large number of pointings. So you certainly have to be careful what you put in there for how long this is going to take to run. But for us, for this example, it's running in a reasonable amount of time. It's still doing something here, making a plan. Okay, and then it has moved us on to the plans stage. So now we have this plan that's called gratings, and this describes the information in the plan. These are all the different pointings that we have, and here it's telling you the number of galaxies that it managed to allocate onto the MSA. So 60 odd galaxies for each of the MSA configurations it has, and then the total weight here is telling you the weight. And then here are the different targets that are shown. If we have, so all targets that are shown that we have in at least one exposure, there's 110 of them. Okay, so this was just for the gratings. We also want to observe with the prism. So we're going to go back and create a similar plan for the prism. So we go back to the planner, and we still have all the same information there. We're going to do the same kind of offsets, but we're going to delete a couple of these, and we're going to change this to the prism. So now we're just doing a prism plan. So the prism MSA configuration is different because the prism spectra are short, and so because of that, you can get multiple spectra next to each other on the same row. So you can get a higher multiplex with the prism than you can with the grating. So if you were really keen on getting the same galaxies observed with the grating and the prism, you could basically take the output from the previous one we just did, where we decided which galaxies are going to be targeted with the grating, and you could then give those much higher priority in your input catalog, so that when we run through and do the prism configuration here, it's going to preferentially select those galaxies that you've already selected to be observed with the grating. So we're not going to do that here. We're just going to use the same thing and just hit generate plan. We're going to call this one prism, and we're going to generate that plan.
So Chris, in the prism mode, you by default there's multiple spectra in a row. You don't have to check.
That's right. Yeah. It doesn't ask you now. Okay. It was in this region here where it said, do you want to have multiple sources per row?
Yeah.
In this case, it doesn't ask you. It doesn't give you the option of overlapping the prism spectra, which is a good thing, because in general, the prism spectra, because they're quite short, have higher signal to noise, and you're likely to be detecting a continuum for a lot of cases, and you really don't want. If you start overlapping the prism spectra, you may as well be using NIRISS and doing slitless spectroscopy.
So how many, can you remind me how many spectra can be put on the same row? 2?
It's up to 4.
Up to 4.
You
Okay.
can place them, at the far extent of the MSA quadrants. You can typically it's between 3 and 4. So you'll see that in the multiplex size here, where now we're looking at 274 targets, and in each configuration it's around about 170. So that's kind of 2.5 times as many galaxies as we got for the grating. Okay, so now to make an observation, the most efficient way of having an observation is that we'll merge the two plans together. We have a plan called gratings and a plan called prism. We'll merge the two. So we merge them both, and we'll call this G plus P for gratings and prism. And we'll make a merged plan. And so this basically does one and then the other of these two plans. And we can then create a single observation by clicking here that does that. So we click create observation, and you can see now we're back in the familiar part of the MPT if you've looked at setting up other observations, where we have NIRSpec multi-object spectroscopy. This is the total amount of time the project's going to take. We have these things we've already entered, and then down here we have the gratings and filters and the exposure sets that show you the total exposure time, etc. here. Okay. What else? On the visit tab here, there's a bit of information about this works. There's a bit of information about the different overheads going into the visit, and then there's also some information here about target selection and the target selection stars, for example. If we have reference stars in your catalog, it'll tell you about it'll show you where they are on the field here, these little crosses. But for phase 1 proposals, you don't have to worry too much about the reference stars. As long as it's clear that there will be enough reference stars in your field, you don't actually have to set up the actual exposure time for the target acquisition exposures. Basically just a regular, just a set amount of overhead is added for target acquisition in the phase 1 process, and you don't have to define the exact amount of time till phase 2. So we'll go back over here to the planner, and the final thing to show you in the last couple of minutes is that there are a couple of ways in which we can visualize how successful our plan has been and the targets we have. So one possibility, we can send the targets to Aladdin. So now in Aladdin, we're showing the observation, which if I make that see-through, you can see the observation has these slightly offset 4-quadrant regions overlaid on our target catalog. And if we zoom in, then some of the sources now, the targeted sources are shown, but it's a bit hard to see which ones they are because of all the other sources in the catalog. So let's delete the catalog. And now if you look, because they're yellow, it doesn't show up very well, but for example, this one here, these are yellow. I can delete all the rest of the sources, and then you just see the yellow now is the sources that we actually have in this particular observation. And the other thing you can do, if we go back to here, is, if I can find it, is click show here. And if you click show, then it'll open up a new window after thinking about it for a little while. You know, these parts of the MPT are pretty heavy on memory for your machine, so try to be using a machine with lots of memory, and obviously save your work frequently, which I haven't done since I made the observation, so I should do that, so that you don't lose anything if everything crashes and hangs. I'll save that again. But now you see what we get is we get a little view with the MSA of, there's different colors here denoting the primary targets and the filler targets, and different ways in which you can understand what's going on. So you can stretch that to make it bigger, but then you can also zoom in. Zooming and panning is a bit tricky with this, but you can do it by right-clicking. So you can zoom around, but you can zoom right up to the single shutter level, and you can actually look. Here's a little 3-shutter slitlet that you've created that has a target in it, and so you can do this. And then, you know, you can really look around and see what it is you've managed to create. You can also look at things on a collapsed shutter view. So here we have, this is basically showing you for the total size of the shutter, how well centered each of your targets is. And you can see that they are spread around kind of uniformly within the region you allowed as expected. And you can, you know, click on individual sources and find out which sources those are, etc. Okay, final thing I want to show you is that you can also send the shutters plane to Aladdin. So this now, as well as showing you the targets you're after, will show you a little 3-shutter slitlet in Aladdin. If I can move around. And then the other thing you could do is you could say, well, actually, I have my image that I selected my targets from here. So I'm going to use that instead to display. So I have this image in the Z band from the UDF. So I'm going to open that, and basically now you can see exactly which galaxies you've targeted, which ones are falling. A lot of these galaxies are very, very faint in the Z band because they were selected from the infrared survey. But if we just change the stretch a bit, you can see, for example, we have this galaxy here. This galaxy is quite large. And you may well see in this kind of case, if you have a large galaxy and it's actually falling into all 3 of your shutters, you may decide, well, I don't want to observe that one because I'm not going to be able to get any background. In those cases where you have the galaxy falling in quite a few, all the way along here, then you have to find a different way of doing background subtraction. Here's a case where you have a much more compact galaxy that's reasonably well centered, and the background subtraction should be a lot easier. Okay, that's about it. The only other thing I wanted to mention is that in the APT, you are allowed to do, if we go back to the observations, you're allowed to do parallel observations with NIRSpec, but NIRSpec must be the prime. So we go back to the observations summary and the observation. You can do a coordinated parallel. NIRSpec must be the prime observation because obviously you have all this complexity in setting up the exact pointing center, so you can't make any other instrument be prime. It has to be NIRSpec, and you set up exactly the same observation the way you have, but then you can select. And the only option that is available in cycle 1 is to select NIRCam imaging. And so if you want to do parallels, you can then, there's a NIRCam imaging tab, and basically for each exposure that you've set up in NIRSpec, you can set up a matched exposure in the NIRCam tab using both the modules and the full subarray and the short wavelength and long wavelength arms. So that is an option that is available if you think your science case can use multi-object spectroscopy and some NIRCam parallel imaging in a nearby field. Okay, so that's all I have today. So are there any questions?
This is a lot to digest, eh? It's a
yeah.
it's a totally new world.
Yeah, I have to add that the JDocs web pages, the Institute, they have a lot of detail about setting up the MSA plans and how to do things. And they also have some training videos as well. So this is just running through one example, but if you want to look at all the different options for what you might want to do, then there's a lot of information there. So obviously I don't expect you to remember everything that I've said today. So do go look at JDocs for more information.
Okay,
I mean,
well,
you know, the key thing is that, you know, we now have spectra of 200 galaxies from 1 to 5 microns in one shot in a single observation. So it's going to be incredibly powerful for being able to do all kinds of different science.
And something I note is that the NIRSpec and the MSA is the only mode where you can, well, you really have a phase 1 and later a phase 2 for James Webb.
Yeah,
right?
That's right. So yeah, the other instruments or modes, it's expected that pretty much everything you specify in the first phase is exactly what you're going to do.
And for those who don't have HST or previous imaging, you can basically program imaging prior to doing the NIRSpec in the same proposal, right?
That's right. Yeah.